Yes, yesterday we characterized complete matching. Any questions? So basically we showed that this condition given by Hall is both necessary and sufficient. Right, so for any subset of vertices, when there are exponentially many subsets of neighbors, the neighbors should be enough, as many as their vertices is. So one side was easy and the other side was by drawing this augmenting path. So in fact, this is an algorithm to find complete matching, which in the case when x and y are both of equal size, you will actually get a perfect match. You repeat this augmenting path. Also, if false condition is violated, if you implement this algorithm, you will also give you the S for which the condition is violated. So you will actually find out that there is no complete matching. Because basically what will happen in this proof is when you implement an algorithm, after a while augmenting path will not exist. And if it doesn't exist, then you know from the first main theorem that you have a maximum matching, and still if the vertices are not all covered, then it only means that we have few neighbors. We find the subset. Anyways, we'll not go into that algorithm. This proof is enough. If you have any questions, you can ask. Okay, if not, then we are almost done with graphs. I'll just do one more thing because it's an important property of graphs, which is planarity. So planar graphs are those graphs which can be drawn on a plane without edges intersecting. Okay, that is the definition. So G is planar if it can be drawn on a paper without two edges intersecting. Obviously except at the vertices. Okay, so example is this graph. Right, so this I have drawn without, so there are 5 edges, 4 vertices, but I don't intersect any 2 edges. If they intersect, then it means that it's a vertex. Right, so 1, 2, 3, 4. What's the example of a non-planar graph, which you cannot draw on paper? Yes, so if I let's say I add this edge. So now there are 6 edges, 4 vertices. Is this planar or not?
Because we can connect one model.
Yes, because you can, instead of this dotted one, the dotted one you can draw like this. Okay, so you can draw 6 edges such that no 2 of them intersect except at vertices 1, 2, 3, 4. Right, so this K4 is an example. Right, so the complete graph on 4 vertices which has 6 edges is planar. What about K5? So what does K5 have? Has so 1, 2, 3, 4, 5 vertices, and if I try to draw the other edges, there will be how many edges? 5 we have drawn, there are 5 more, right? So let's draw this. This is fine. So I have drawn 2 more. 3 remain, right? Can you draw them? No, you can obviously draw them. Without intersecting, you can draw like this. And what else? This. Sorry? Yeah, so what remains now? There is still something remaining, which is 2, 4, right? Now, can you draw this, can you redraw the graph so that this edge is also non-intersecting? Do you have a proof of this? Because maybe I tricked you and I started in a bad way. Maybe there is a completely different orientation. Right? So I leave this as an exercise. Try all possible ways during the Dussehra holidays and show that K5 is not planar. Right? So amongst all possible configurations, none of them will work. There will always be last edge which will require an illegal intersection. It's illegal because this 3, 5, 2, 4 intersection is not a vertex. Right? There are no 6 vertices, there are only 5 vertices. So we don't want to avoid that, and that cannot be avoided. So yeah, usually graphs are non-planar. Planar graphs are very rare. So when you convert a country map into a graph, is it planar or not? Yeah, so that is the special property of political maps, that they are planar. And the result that I mentioned before, this Apel-Haken result, 4-color theorem, it's for planar graphs. So planar graphs are 4-colorable. That's the major theorem. Which we have mentioned many times before, but there was nothing special about political map except this thing, that it's planar. So G planar implies that the chromatic number is at most 4. Okay, that's one major property. Okay, last thing is there is another example which is K33. K33, is it planar or non-planar? So 1, 2, 3. So you can draw these, and you can draw these. And what else can you draw? So 1, 2, 3 also you can draw. What else remains? 2, 2, 3. No, now I cannot. Oh, wait, let us do it properly. 4, 5, 6. Yeah, now what? 2 to 6 I've already drawn. No. So what remains is now 3 to 4. That's a problem.
So we can draw the 2 to 6 line below the 3 and then 3 to 4.
Yeah, you can try all these possibilities during your vacation. But what will happen is this is also non-planar. Okay, so both K5 and K33, these are non-planar examples. These are famous examples because there is a theorem that under certain transformations, any non-planar graph can be reduced to either K5 or K33. Okay, so these two graphs are the source of all kinds of non-planarity. So the meta theorem is that G is non-planar, then either K5 or K33 is embedded. I won't define this because this theorem you are not expected to use this in this course. We will not prove this, but it can be shown that, it is clear, right, that if a subgraph is K5, then the graph is non-planar, right? So that's the if and only if condition. So I'm saying that in general, actually, non-planarity will always be witnessed by either K5 or K33. Both the directions are true. These may not be subgraphs, but there is a way to embed them, which I am skipping. And final thing I want to show is Euler's formula. Which is a very old formula, but it reappears in many areas of mathematics in various forms. It's very fundamental. So what it says is that if G is a connected planar graph, then I'll write it in short form. So V minus E plus F is equal to 2. So what are these? So V is the number of vertices. E is the number of edges. Maybe I should write in short. Because that will confuse with the set. And E is the number of edges. F is the number of faces. Okay, so the correct way to interpret this is that if you look at dimension 0 things, dimension 1 things, and dimension 2 things, then they satisfy an equation. Okay, it's very important in math because there are topological interpretations which apply for all dimension and all surfaces, which generalize this formula. So here you know vertices, edges. What are faces? That needs definition. What are these dimension 2 objects that I am talking about? So faces are basically regions that your graph has. So faces or regions in which the plane is divided by the graph. So for example, in the case of a vertex, the number of regions is what? the plane is still there, right? The plane has not been divided into two regions. So okay, let us just interpret this formula. So in the case of a point, vertices is 1, edges are 0, faces is 1, so you have 1 minus 0 plus 1. In the case of a line, what do you see? You have 2 vertices, 1 edge, how many faces? It is still 1, right? Because the line doesn't really divide, I mean, it's not an infinite line, it's a line segment that doesn't really divide the plane into 2 parts. First time that happens is by a triangle. Right, then you have an inside region and there is an outside region. So you have now 2 faces, edges 3, and 3 are the vertices, so you get 2. Okay, and so on. So you can, in general, you can show, Euler showed that for any planar graph, this property is true. How do you prove this? The proof is actually in these examples. What we are doing is we are just, okay, maybe I jumped an example here. There is one more example where there are 2 edges. So in this case, how many regions are there? Yeah, in this case there is 1 face, 2 edges and 3 vertices. So this is also 2. Yeah, so 0 edges, 1 edge, 2 edge, 3 edge, and you basically induct on the edges. Okay, the proof is an induction on E. So I have shown you 4 base cases, and you can just continue the proof by induction. Induct on E. It's a simple proof. Basically what will happen is that when you add an edge, either you will add an edge by adding a vertex, so then you will be going out of this previous graph, in which case face will not be added. New face will not be added. So V minus E will remain the same. Or you will not be adding a vertex, you will just be adding an edge between 2 existing vertices. In that case, what will happen? E grows by 1, but F also grows by 1. So then also it is 2. Okay, so you just have to analyze V minus E or F minus E. It's an invariant. So this is an amazing result, and it holds for all kinds of, all higher dimensional objects you can prove similar things. But yeah, if you have any questions, you can ask. Else I will move to a new topic. Anything about graphs? Okay, so now you are an expert in graph theory. So hence we will move to a different subject, which is called number theory. Yeah, saying that this is the number theory may be too much. We'll do very simple things. So, goes without saying that we will study properties of numbers. And it is considered to be the best area in maths. So in the whole of maths and in the history of maths, this is considered to be the most beautiful part. you don't have to take my word for it. If you analyze the mathematical literature and especially modern maths, much of the methods have been invented to solve number theory problems. Okay, it may not be evident now, but even calculus was invented to actually solve, and complex analysis was invented to solve number theory questions. So almost everything is actually there because of questions or conjectures in number theory. To answer number theory questions, including things like you look at system solving for linear systems, for quadratic systems, and so on. Those things were really, they came from our very early attempts to study properties of numbers. So the motivation was always from there. It's not very surprising because numbers were the first things that were invented. So people wanted to study their properties first before anything more complicated. But most of the properties of numbers are very difficult, so one has to invent a lot of things. Most of them nothing to do with the numbers, and then maybe you get some insight about the original question. So yeah, the things we will study here, they are used a lot in practical computer science and obviously in theoretical computer science. So let's start with some basics. So the first thing is which we will need, and obviously you know it, is integer division. So the result I want here is the following. That given integers a and b, or numbers, I'll always mean integers. So given numbers a, b, we can uniquely find the quotient. So a equal to qb plus r, such that q, r are integers, in fact natural numbers. I should say here also maybe. Okay, let's specify, sometimes it's important. Such that the remainder is between what? Yeah, if I want uniqueness, then I have to say we have to specify some range, because otherwise the possibilities of q and r will be infinite, could be infinite. So we specify the range like you do in school, that r is between 0 and b, the absolute value of b. In fact, for divisors, you should think of divisors as positive. They cannot be 0 or negative. So in that case, we are just talking about, let's just specify that. Assume divisors to be positive. So the remainder is between 0 and b minus 1. What is the proof of this? Well, is it clear that q and r exist? That is just the long division algorithm. Now, why is it unique? So there are two parts here. First part is the existence. This follows from long division. Which I hope you can do manually without using a computer. Given two integers, you can do long division, right? You basically incrementally find the digits of Q. The most important digit, then the second most important, and so on. You can do that. It's a very fast, to implement on a computer, it's a very fast algorithm. And then it will halt when you reach a remainder which is between 0 to b minus 1. So clearly it exists, there is a fast algorithm. But why is it unique? Why do you always get the same R? Why can't some other algorithm give a different R? R prime. So if you get a different R, then what does it mean? QB plus R is equal to Q prime B plus R prime. Would that be a problem? Why? Yeah, so this will actually mean that R minus R prime. Yeah, let me use the division notation already. That B divides R minus R prime. It will always mean this, that B divides. Okay, it is a asymmetric statement or symbol. The left hand side should divide, the right hand side is what we mean. So from this equation, is it clear that B has to divide R minus R prime? That's by the definition of division of integers. Is that a problem? Well, both R and R prime, by the hypothesis, they are 0 to b minus 1. Right? So which means that this R minus R prime absolute value is less than b. So what is an integer, positive integer that b divides between 0 to b minus 1? It's only 0. So which means that R minus R prime is 0. Right? Which is a contradiction, or you can say proves uniqueness. Okay, so this is the reason why that one algorithm that we have learnt is enough, because it gives the exact answer. There is no other answer. Okay, so these are small beginnings, but you can do a lot with division. So yeah, let's just put some definition. So we say B divides A if the remainder is 0, or maybe in the above notation A divides B if R is 0. If R is 0, and we denote this as B divide A notation. Right, so example is does 7 divide 101? Should not. So that we write like this. Does it divide 105? Yes, so we write like this. Okay, so that's not divides, the second one is divides. And based on division, what you can define is greatest common divisor. So GCD of A comma B written as like this, where usually we will skip the GCD keyword and we'll just write brackets. So bracket A comma B, this operator means that we are interested in the GCD, greatest common divisor, which again, as you know, is the largest C which divides both of them. The largest number such that C divides A and C divides B. Will it always exist? Well, you know that 1 always divides A and B, right? So there is only a finite possibility after that. So the largest will exist. It will be unique. So that is called GCD. And if it is 1, we say that the numbers are co-prime. The definition is if AB is 1, then we say A co-prime to B. Okay. So the thing in computer science is that these numbers we deal with in any application, especially in cryptography, they are very, very large. So for example, this A and B will not be like this 7 and 105, but they could easily have 500 digits or may have 1000 digits. So 1000 digits means that it's around 10 raised to 1000, right? This, although you can write it easily on a page, but the value is extremely high. So if you are given 2000 digit numbers, A and B, how do you think you will compute GCD using this definition? Because this definition requires you to go from 1 to A to find C, right? Or you have to factor A and B, and then by factorization you have to find C. None of which will work because there are 10 raised to 1000 iterations, which is like eternity. The program will never stop. Even if you waited till the end of the universe as estimated, still program will not stop. So how do you think you will compute GCD for such big numbers? This you must have already done in ESC 101. There is a recursive algorithm, right? Did you also see the proof of that? Okay, then we'll do it. So the basic idea for GCD is as follows. Suppose you have to compute GCD of 5 and 11, which you will already know it's 1 because these numbers are so small you can immediately do in your mind. Systematically, what we will do is we will use division. So we'll write 11 as this, right? From which, what do you learn? You see that 5 is dividing the first summand, so we can drop it. So this GCD has to be the same as the GCD of 5 and 1, right? Which is 1. If 1 sits, then answer is 1. So this is the thing that we will use repeatedly. Or if what may have happened is, suppose you had 5 and 12, so then you write 5 times 2 plus 2, so then it becomes 5, 2, but still we have not reached 1, So how do you divide next? Yeah, now you do in the opposite direction. So you write 5 as 2 cross 2. Plus 1, 2, which is then 1 comma 2. So now you have reached 1, so you can halt and say that again the GCD is 1. Right, so although you can short circuit this because these numbers are small, but I don't want to do that because you want to give an algorithm which works for 1000 digits or more. So you don't want to use cheap tricks, you want to do it systematically. So systematically this division can go on in either direction and you will reach ultimately 1, or there may be an example where you have like the following. What happens with 6 and 9? So you write 6 as 6 times 1 plus 3, which gives you 6, 3. Then you divide, so you get 3 times 2 plus 0, which is, you can drop 3 cross 2, so it's now 0 comma 3. What is the GCD of this? Right, so we will be looking for either 1 or 0 in the end. Okay, that's where you want to reach. Either you reach 1 and halt, or you reach 0 and halt. When you reach 0, then you will get some interesting GCD. When you reach 1, then you will get 1 as GCDs. Right, so this is what turns into your ESC 101 algorithm. So the property here that we are using, main property, is that A comma B, like we had this division QB plus R. So you write A as QB plus R by the first division algorithm. So Q and R will be unique, and then you drop QB part. Now why is this progress? Why is R comma B better than A comma B? Yeah, because the numbers are smaller. So previously, say you had A greater than or equal to B. E was the bigger one, which is why you divided it by B. Now R is less than B, and so previously the maximum was A, now the maximum is B. Okay, so in the case when A was strictly bigger than B, then you are making progress. So this is the recursive call. It's a recursive algorithm. You can prove this as an exercise. There is some proof needed because the GCD was defined via largest C that divides both. So when I drop QB, you have to argue that the largest C that divides R and B is the same as the largest C that divides QB plus R and B. Right? So that's a one-line proof that you have to write. And so the pseudocode is the following, which is the Euclid's GCD algorithm. From many years ago. Not exactly clear whether Euclid even invented this, but certainly wrote this down. So this is the oldest algorithm known and the first interesting number theory result, which is now used everywhere. Not in this form, but in many other forms also. So this is pseudocode is you check if B is 0. If B is 0, then in that case, you have already reached the base case, right? So you output what? And yeah, so we are computing GCD of A comma B. That's the pseudocode for. So if B is 0, then you just output A. If B is 1, then you output what? Then you output 1. Doesn't matter what A is. If B is 1, then you get the answer as 1. And last is so there are 2 base cases and then a recursive call. So compute, in all other cases, you have not reached the end. So what you have, base case, so what you have to do is you have to make the A comma B smaller. So you do long division. So let's say A is bigger. So in that case, you compute A equal to QB plus R. And then output, what's the call? Yeah, so let's assume the invariant is A greater than B, greater than or equal to B. So here then we should send what? R comma B, B comma R. Right, so then it goes back and if there is a need, it will divide B by R or it will go to the base case and output directly. Right, so this is the algorithm. It's proof of correctness you have to show formally that I'm skipping. It's based on the previous identity. You basically have to show in the proof that the invariant condition is this. So every recursive call is correct. Assuming that the recursive answer is, the answer of the recursive call is correct, the algorithm is correct. So it's basically a proof by induction. Okay, show the induction step, show the base case. So prove its correctness by induction. Is that clear? Okay, I guess we've seen enough examples, so I don't need to exemplify this. So let's move on. So one property of this is, or let's say, the underlying equations in this algorithm they are important to prove another result. So by underlying equations, I mean let us keep track of all these recursive calls. So when you call GCD A comma B, then you get the definition of Q1 and R1. Okay, next time you will call R1 comma B or B comma R1. So that will give you the definition of Q2 and R2 and so on. So let's say there are k steps, so you reach Rk minus 1, Rk, which will give you the definition of I think k plus 1. And yeah, so this is supposed to be the last step. So here the remainder will come out to be 0. Actually, when I said stop at 1, we could have continued. Let's change this. We could have written 5 cross 1 plus 0, and then we reach 0 comma 1. Right? We could do that as well. So we can say that we will always reach 0. Same thing here. So 0 is always reached then. Let's stick with this invariant. Right, so here actually base case is only 1 then. So this is the 0 that will be reached in the end. And that's the last step. So here you return the value RK, that's the GCD. Okay, so why have I written these equations? Because this proves a major property of numbers, which is that the GCD is a linear combination of A and B. Do you see this? So this actually is important for the following theorem, which is called Bezout identity. That there exists numbers alpha and beta such that the GCD of AB is equal to alpha A plus beta B. Do you see this from these equations? Note that this is highly non-trivial, because let's go back to the example. 5 and 11, they have GCD 1. Right? So what we are claiming now in Bezout identity theorem is that 1 can be written as an integral combination of 5 and 11. Right? Which is very non-trivial, because 5 and 11 are both more than 1. And if you just take the difference, that will not work, because then difference is 6. So you have to actually work harder. You have to take 2 times 5, that is 10. Subtract that from 11, that will give you 1. Right? So it's sorry? Yeah, so the integral combination is minus 2.5 plus 1.11. Right? That is minus 2 times 5 and 1 times 11. The sum is 1. 6 and 9, the GCD is 3, so you have to write 3 as a combination of this, but this is easy because the difference is already 3. But yeah, in general, when you have very big numbers, random numbers, it's highly non-trivial how you will combine them so that you get 1, for example. Right? This is a very non-trivial property, is only true because of this algorithm. And the claim is that if you look at these equations, you will be able to prove it. Do you see it? Okay. Then you are too clever. I don't think half the class sees it. So let us look at the simple case when the division step was only the first one. There were no subsequent steps. So in that case, what you are getting is that R1 is a combination of A and B, right? Now suppose, so R1 is the output, and you have shown that R1 is a combination of A and B, namely 1 times A minus Q1 times B equal to R1. Now suppose the algorithm has 2 steps, output will be R2. So you use R1's combination and substitute it in the second equation. Right? That will give you combination of A and B is R2, right? And so on. So this is also a proof by induction on the steps, division steps. So R1 is a combination of AB yeah, let's just write like this, and then R2 is a combination of BR1, but then you can use the previous identity and substitute to get minus Q2A and so 1 and Q1, Q2 B, right? And so on. So ultimately you will get that this RK by induction, that's the induction step. So formally you have to say this, that in the base case it's obvious, R1 is obvious, and then other RIs you assume that it's true up to RI and you show it for RI plus 1. So you ultimately get it for RK, this alpha A plus beta B. Okay, so those equations in kind of in reverse will give you Bezout identity. Is that clear? So this is a highly non-trivial statement, and this also shows that your algorithm actually does more than what was asked. It not only computes GCD, but it also computes the linear combination. It computes alpha and beta. Right, so that's called, what is it called? So this is the extended Euclid GCD algorithm. That alpha, beta are efficiently computable. This course is not about efficiency, so this I'm not defining, but basically the same pseudocode that was written also computes alpha, beta. Right, that's the proof above. And as you have experienced in ESC 101, it's a fast algorithm. So that's all we are saying here. So for you, an exercise is to find out the worst possible K. So if A, B are n digits, how large can K be? To n. Why not n? Yeah, so what he's saying is that you have to show that in 2 steps of the algorithm, which is well, let's just work with this equation. So in 2 steps of the algorithm, which is R2, the remainder R2 that you will get, this will be less than half of I guess A. Okay, so the largest number that was given to you in 2 steps, you would have reduced the maximum by half. But it's only half, right? So you don't get 2n. You can get more than 2n. Maybe just to make your answer correct, let me change the question so that you are not disappointed. So let's take A and B n bits. So A and B in base 2 have n digits. And then since in 2 steps, if you show that the number is being halved, so basically the string length is reducing in every 2 steps. So ultimately at 2n steps, you will be done. So you have to show this and construct an example. They show that there are examples of AB where 2n is required. Okay, this is to do with some recurrence we did earlier in the course, which is exactly Fibonacci sequence appears here in the analysis. So construct those examples, which now justifies efficiency because everything in computers, the numbers are represented in bits. So if you have instead of 1000 digits, I say 1000-bit numbers, then for 1000-bit numbers, you just have to run this for 2000 steps, 2000 iterations. In every iteration, all you are doing is division, right? Which is very fast. So overall, this is like 2000 times maybe 500. So 2000 times 500 steps is what your computer will invest in this, which is extremely fast by today's standards. So this can be done in few milliseconds. So in few milliseconds, you can compute GCD of extremely large numbers that have value like 2 raised to 1000. Right? This is much better than what the definition said of GCD. So it's a completely different way to work with GCD than the definition. Yeah, so another property is, so once we have Bezier identity, any questions till now? So once you write, what was this, GCD alpha A plus beta B. What I want to show is that this alpha beta is in some sense unique. Is it? Yes or no? No, right now they are not. Because right now, why are they not unique? What is the example? Yeah, so basically what you can do is the alpha you can perturb by anything times b. You can perturb alpha by sb, where s is arbitrary integer. And how will beta change? Right, this is also an identity. So if alpha A plus beta B is your GCD, then you can perturb alpha by a multiple of B, and you can perturb beta by a multiple of A. And very easily you get another alpha prime beta prime pair. So Bezout identity is not unique. There are infinitely many possibilities. So how do you think we can make it unique? Sorry?
We can replace alpha with GCD of
Alpha by the GCD of what? No, say the GCD of A comma B is 1. So in that case, 1 equal to alpha A plus beta B, there are infinitely many alpha beta. Right, which also is kind of a surprise, although this identity makes it trivial. But it is a surprising thing that Bezout identity, there are infinitely many possibilities of expressing 1 with the same AB. Yeah, but how can you make it unique? What conditions can you put? Sorry? Alpha minus beta. I don't think that has any effect. It is nothing to do with GCD. Alpha plus SB and beta minus SA also have GCD 1 generally. Still you will have two solutions or infinitely many solutions. No, what you have to do is you have to say that alpha is the remainder by B and beta is the remainder by A. Then it will work. So let's do that. Oh, we already are. Time is up. So let's do it next time. So this is the unique Bezout identity. So as always, let's assume A greater than B greater than 0. Then there exists unique alpha beta. Such that GCD is alpha A plus beta B. The conditions are, you say that alpha is less than B prime, beta is negative, minus A prime plus 1, and A prime is basically A divided by the GCD, and B prime is B divided by the GCD. This is too complicated to read, so let's make A comma B GCD 1. Let's assume A and B are co-prime. So in that case, what we are saying is that 1 equal to alpha A plus beta B for co-prime AB will have unique alpha beta such that alpha is smaller than B in magnitude and beta is smaller than A in magnitude. Okay, so it's this cross relationship. You impose alpha to be smaller than B and beta to be smaller than A. And then you can show that they exist and they exist uniquely. Okay, this you can try, we will finish it next time. Any questions?